Good morning. Next is reactions of aldehydes and ketones. The first reaction is nucleophilic addition reaction. Okay. In this class, we are discussing the reactions of aldehydes and ketones. The most important reaction that is given by aldehyde and ketone is nucleophilic addition reaction. So let us go through the nucleophilic addition reaction. We know that the carbonyl group in aldehyde and ketone, this is the carbonyl group present in aldehyde and ketone. This carbonyl group is polar in nature. That means due to the electronegativity difference between carbon and oxygen, carbon is slightly positive and oxygen is slightly negative due to the electronegativity difference, or we can say that the CO group is polar in nature. Carbon is slightly positive and oxygen is slightly negative. And what do you mean by nucleophilic addition? When a nucleophile is attacking, you can see that if it is a nucleophile, you can see that the nucleophile will attack on this positively charged carbon. That time what will happen to the double bond? One of the bonds will be shifted to oxygen. Okay, this is what is known as a nucleophilic addition reaction. The nucleophile can attack at the positively charged carbon on the carbonyl group. Example, if you take aldehyde R, C double bond or H, this is aldehyde, react with HCN. HCN means H plus and CN minus. Therefore, what will happen? Here you can see that in CO group, carbonyl group, carbon is slightly positive and oxygen is slightly negative. Here you can see that the CN, this is our nucleophile. The nucleophile will attack at the positively charged carbon. Then what will happen to the double bond? One of the bonds will be shifted to oxygen. So we get R, C, here it is H, and here you can see that here it will come CN, and here it is, what is that, O minus, O minus. Then in the next step, this H plus will join with the O minus and it will change into OH. This is what is called a nucleophilic addition reaction. The nucleophile will attack at the positively charged carbon. The bond is shifting to oxygen. Then the positive part is joining with that oxygen. This type of reaction is known as a nucleophilic addition reaction. And when we discuss the nucleophilic addition reaction, the order of reactivity of aldehydes and ketones towards nucleophilic addition reaction, you can see that formaldehyde HCHO, this is most reactive towards nucleophilic addition reaction than other aldehydes RC double bond O H. And you can see that RC double bond O R, this is ketone. Ketone is less reactive than aldehydes towards nucleophilic addition reaction. Why ketone is less reactive towards nucleophilic addition reaction when we compare with aldehyde? Or we can say that aldehydes are more exposed towards nucleophilic addition reaction than ketone. The reason is very simple. We can see that when you compare aldehyde and ketone, here in ketone, the CO group is suffered by steric factor. The CO group are, you can see that there is a steric factor. Steric factor is playing a major role in the case of ketone. That means the CO group, this attack by the nucleophile, here is our nucleophile. The attack of the nucleophile on the carbonyl group will be hindered by the bulkier alkyl group, the bulkier alkyl group. So therefore you can see that ketones are less reactive towards nucleophilic addition reaction when we compare with the aldehydes. And in the case of, when you look at this series, you can see that in the case of formaldehyde, apparently there is no steric factor, because the CO group is attached to only some very small hydrogen atoms. Therefore the steric factor has no role in the case of of formaldehyde. Therefore, formaldehyde is highly reactive towards nucleophilic addition reaction. When we come to aldehyde, you can see that there is one alkyl group. That means there is a chance of steric effect. And when we coming to ketone, there are two alkyl groups. That means in the case of ketone, the steric factor is more important. And one more point, you can see that when we compare the nucleophilic addition reaction, the reactivity of nucleophilic addition reaction of aliphatic aldehyde and aromatic aldehyde. Look at here, aliphatic aldehyde and aromatic aldehyde. When you compare the reactivity of aliphatic aldehyde and aromatic aldehyde towards nucleophilic addition reaction, we can see that aromatic aldehydes are less reactive towards nucleophilic addition reaction. And why aromatic aldehydes are less reactive towards nucleophilic addition reaction? Look at here, aromatic aldehyde means example we can take benzaldehyde. See, double bond OH, this is benzaldehyde. Okay, so ring CHO. Okay, what is benzaldehyde? Actually, this is benzaldehyde. Actual structure is like this. And one factor, okay, now the nucleophilic addition reaction means the nucleophile has to attack this carbonyl carbon. Okay, and we can see that when you compare the reactivity of aromatic aldehyde and aliphatic aldehyde, aromatic aldehyde is less reactive. One factor you can see that due to the presence of bulky phenyl group, that means why less reactive? One is steric factor. The steric hindrance offered by the phenyl group. Because of this phenyl group, it can offer a steric hindrance. That is the one reason why aromatic aldehydes are less reactive towards nucleophilic addition. First reason is steric factor of the bulkier phenyl group. And in the second factor, what is the second factor? We can see that as we have discussed, we can see that the carbonyl carbon, this is carbon is delta positive and oxygen is delta negative. Since this carbon is slightly positive, what will happen? This pi bond will be migrated to here. That means between these two carbon, that time what will happen to the double bond? One of the bonds will be shifted to oxygen. So we get a resonance structure like this. Okay, it is like this. Now here it will become double bond CO minus. Here it is our H, and here it is double bond. Since the bond is breaking from this carbon is getting a positive charge, correct? This is like this, breaking from this carbon is getting a positive charge, and okay, and in the next stage it will come here, and it will continue like that. That means by resonance we can see that the positive charge on the carbon atom is reduced. Here you can see that there is a slight positive charge is there, but since this pi bond is shifting to here, what will happen? This positive charge is removed. That means that positive charge is removed. Therefore, the ability of the nucleophile to attack on this carbon, its ability will be reduced. Correct? Because the positive charge is reduced, therefore the nucleophilic attack will also be reduced. That is the second reason. What is that? The carbonyl group, this CO group, the carbonyl group can be stabilized by resonance. Okay, that means the positive charge is reduced by resonance because the pi bond is shifting here. Therefore, the positive charge on the carbon is reduced by the resonance. Therefore, the attack of the nucleophile will become difficult. These are the two reasons why aromatic aldehydes are less reactive towards nucleophilic addition reaction when we compare with the aliphatic aldehyde, because in aromatic aldehyde, the first factor is bulkier phenyl group, that means steric factor, and second factor, the positive charge on the carbonyl carbon is reduced by resonance. Therefore, the attack of the nucleophile will become difficult. Clear? Now, let us discuss some examples for nucleophilic addition reaction. First one is addition of water. First example is addition of water. Addition of water. This reaction is known as hydration. Hydration. Okay. Look at here. First I am taking formaldehyde HCHO. React with water. Water is HOH. Correct? And you can see that the water can act as a nucleophile. What is the reason? Oxygen is having lone pair electron. Oxygen is having lone pair electron. You can see that one lone pair will attack on this positively charged carbon. This is slightly positive and this is slightly negative. So when the oxygen lone pair is attacking on this carbon, the bond, one of the double bonds will be shifted to oxygen. So what we get? We get a structure like this. H. Here it will become OH. And H, and here it is our O minus. And since this pair of electron is donated to this carbon for making a bond, what will happen to oxygen? Oxygen is getting a positive charge. Oxygen is getting a positive charge because this pair of electron is used for making a new bond. That means this pair of electron is donated to carbon to make a new bond. Therefore, oxygen is getting a positive charge. And what will happen? The next step. In order to regain the stability, what will happen? This bond, this OH bond, breaks from hydrogen and will go back to oxygen. That means the lone pair electron will come back to oxygen, and that means here what is removed? Minus H plus, minus H plus. H plus is removed because the H is going without its bond pair electron. Only the H is going. That means H plus is going. Minus H plus. That H plus will join with this O minus. That means minus H plus and plus H plus. Okay. What do you mean by minus H plus and plus H plus? Minus H plus means H plus is removed from here. Plus H plus means that H plus is adding to this oxygen. So what we get? We get a structure like this. CH. See this carbon, there are two hydrogen, and here is OH. So this OH, and here also will become OH. Correct? This H plus is joining with the O minus. Okay. And this is known as formaldehyde hydrate. Formaldehyde hydrate. Or you can call it as methane diol, formaldehyde hydrate, or this is known as one carbon alkane, methane diol. Okay. Another example, if I take this is formaldehyde. When we take formaldehyde, we can see that here the product formed formaldehyde hydrate. This product formed is about 99%. That means about almost completely the formaldehyde is completely changed to formaldehyde hydrate. Of course, this is a reversible reaction. Okay, that means about 99% of formaldehyde hydrate is formed. Now I am taking acetaldehyde. Okay, so that means CH3, C double bond OH. Again, acetaldehyde is reacting with water, HOH. Same reaction will occur, same reaction. Okay, and what we will get? We can see that this lone pair of electron will attack here. Here it will be shifted. Then this H plus will be come to oxygen. So what we get? We get CH3. Okay, here is also C, and here is H. This H, C, CH3H, and here it will become OH. Here also will become OH. Same mechanism. Okay, minus H plus and H plus. And here you are getting, what is the name of this compound? This is formaldehyde hydrate. This is called acetaldehyde hydrate. Okay. when you see the percentage of acetaldehyde hydrate formed, we can see that it's only 50%. This is only 50%. That means only 50% of the acetaldehyde is converted to acetaldehyde hydrate. Or another name of acetaldehyde hydrate is ethane, 1,2-carbon alkane ethane diol, 1,1-diol. Anyway, leave that. Acetaldehyde hydrate, and what is the percentage of yield? The percentage of yield is 50%. Why there is a difference between formaldehyde and acetaldehyde? Formaldehyde is giving 99% yield, while acetaldehyde is giving only 50%. What is the reason for that? Okay, look at here. In the case of acetaldehyde, we can see that there is alkyl group, this alkyl group. And this alkyl group is what type of group? Electron donating group. That means this is electron donating group. Therefore, this electron donating group, what will happen? We know that the carbon is slightly positive and oxygen is slightly negative. If there is electron donating group, what will happen? Which will reduce the positive charge on this carbon. Electron donating group will reduce the positive charge on the carbonyl carbon. That means electron donating group will stabilize the carbonyl compound. This will be stabilized by reducing the positive charge. When the charge is reduced, what will happen to that compound? That compound will become more stable. That means due to the presence of electron pushing group, plus I effect of alkyl group, what will happen to the positive charge on this carbon? The positive charge is reduced. Therefore, what will happen to the carbonyl compound? This carbonyl compound is more stabilized, more stable. Therefore, what will happen? It will have a less tendency to change into hydrate form. It will have a less tendency to change into hydrate form. That is the reason the percentage of hydrate is only 50%. Okay, or we can say that when the positive charge is reduced, if there is an electron pushing group, what will happen to the positive charge on the carbon? Reduce. Therefore, the attack of the nucleophile will become difficult. That means you can see that the equilibrium is almost in a balanced condition. Acetaldehyde is 50%. The remaining 50% will be our acetaldehyde only. Okay. Now, but here that effect is not there. That is the reason we are getting formaldehyde about 99%. Now we are taking a ketone. Okay, let us take a ketone. Look at here. In the case of ketone, CH3, we take acetone, CH3, CO, CH3. Acetone again react with HOH, same reaction. Okay. Is attacking, and okay, we are getting what we get. You can see that here CH3 and one more CH3. Here it will become OH, and here also OH. The product, the yield of this product is only 0.14%. Only 0.14%. What is the reason? The reason is very clear to you. What is the reason? Because in the case of acetone, there are two electron donating group. Here is alkyl group and here is also alkyl group, which will highly reduce the positive charge on the carbonyl carbon. Therefore, this will be highly stable. This ketone, this is highly stable. This will become stabilized due to the presence of the carbonyl compound is stabilized due to the presence of two electron donating group. Therefore, it will have a least tendency to change into the hydrate form. Okay, that is the reason only a 0.14% of hydrate only will be formed. Okay, that means here you can see that and another factor in this case, steric factor also. One is what is that electron pushing group will reduce the positive charge on the carbonyl carbon. Okay, that means it will stabilize the carbonyl group. Okay, that means stabilize the carbonyl group means it will have more tendency to stay as carbonyl group only. You don't want, or it has least tendency to change into hydrate form, more tendency to change remain as carbonyl compound. That is the one reason. And second reason, you can see that due to the presence of this alkyl group, steric factor is also important. These are the two reasons why the percentage of yield is reduced to 0.14% in the case of ketone. Hope you follow these factors which I have discussed, and we will continue in the next class. Thank you.